Thank you. First of all, thank you for the opportunity and thanks to Tofik for all the communications. So I'll talk about this stability of Plethysm coefficients. So let me start with vector partitions. So what are vector partitions? So you take a vector alpha, alpha 1, alpha 2, alpha n, and you decompose the alpha as sum of non-zero vectors with non-negative integer entries. Of course, you ignore the order. So for example, this vector 2, 2 can be written as 2, 0 plus 0, 2, 1, 0 plus 1, 2, and so on. So this 2, 2 vector has like 5 vector partitions. So we will see why combinatorics of vector partitions is important for us. So more notations. So if alpha is a vector, then mod alpha will denote the size of the vector, which is summation alpha I. And by Pn alpha, we mean the cardinality of set of all vector partitions of alpha with at most n parts. P alpha means we are considering all the vector partitions without any restriction. By Pnm, we mean exactly n parts, all the vector partitions with exactly n parts, where all parts have exactly size m. And by P greater than or equal to 2 lambda is all the vector partitions where all the parts have size at least 2. So these notations will be useful for us. Okay. So some basic examples of symmetric functions, which will also be important. So by pkx, we mean the power sum symmetric functions. So you take each variable and you raise them to the power k and you sum them. And if you permute xi's, it will not change. So it's a basic symmetric function. So now what is Plethysm? So I will not go into the technical definition of Plethysm. It is enough for us to understand that if you take any symmetric function, if its Plethysm is with pk, it is just replacing each xi with xi to the power k. That is the Plethysm of f with pk. And then what is this complete symmetric function of degree m? This is the sum of all the monomials of degree m. Sum over x to the power alpha, where mod alpha is m. By x power alpha, I mean x1 power alpha 1, x2 to the power alpha 2, and so on. So what will be the Plethysm of pk with hm? In hm, you replace each xi by xi power k. And similarly, you can define hm Plethysm hn. Yeah. And what is capital H? So capital H is the sum of all hi's. I is running from 0, 1, 2, 3 up to infinity. So this is not really a symmetric function technically, but it is in the completion of the ring of symmetric functions. And then what is this hn Plethysm capital H? So if you look at the monomial expansion of that actually is connected to the vector partition function very naturally. So what is the coefficient of x to the power alpha in the expansion of hn Plethysm H? That is just vector partition of alpha into at most n parts. So remember, alpha is a vector, and by p and alpha we mean the cardinality of set of all vector partitions with at most n parts. So this monomial expansion is easy to write. Okay. So now Schur functions. So for each lambda, we can define Schur function. So how do you define it? You take a partition, you take the Young diagram. For example, I have taken 2, 1, 0. You take the diagram, and then you fill the diagram with the prescribed rule. So what is the rule? So you have all these alphabets 1, 2, 3 up to infinity. You fill them in the following manner. The numbers in a row is weakly increasing, and numbers down the column is strictly increasing. And corresponding to each diagram, so you have weights, this weight vector alpha 1, alpha 2, alpha 3, and so on. So what is alpha I? Alpha I is the number of occurrences of I in a particular semi-standard Young tableau. So these tableaus are called semi-standard Young tableau. And what is Schur function? So basically it is sum over x to the power weight of t. So you raise x to the power weight of t and you sum over all possible semi-standard Young tableaus. And you can check that these are actually symmetric functions, which may not be so trivial, but not so hard. You can check that these are symmetric functions, and it is a well-known fact that they form a basis for the ring of all symmetric functions. So if you take any symmetric function, you can expand them in the basis of Schur functions. Okay. Now, here's the interesting thing. So in 1950, Fuchs made an interesting conjecture that you take n greater than m, and the conjecture says that hm plethysm hm minus hm plethysm hn has to be Schur positive. So that means if you expand the symmetric functions with respect to the basis of h lambda, all the coefficients are non-negative integers. Okay, so there's a weaker version of this theorem, so which was proved by Bowman and Paget in 2022. So they say that you take any partition lambda and you take your m in pq to be large enough. So precisely your m in pq, take them to be larger than the size of lambda. And then if you look at this padded partition, lambda mn, so basically you fix lambda and then you pad over the first row of lambda, you pad a single row so that the whole size becomes mn. And then using the representation theory of partition algebra, they are able to conclude that the coefficient of s lambda pq in hq hp is same as the coefficient of s lambda mn in hn hm. So it implies that when your m and pq are large enough, so then lambda if m and pq are large enough, then they do not really play any role. They become constant once you fix lambda. So that was proved using the, as I said, that was proved using the representation theory of partition algebra. But I believe there is a much simpler proof which I'm going to give a sketch of in this lecture. Maybe inherently my proof may be connected to their proof, but I think there is a very neat and clean, there is a very short way to see that why this is true. So I'll come to that. Okay, so now let's talk about another thing, which is restriction coefficients. This is another open problem in algebraic combinatorics and representation theory, that if you so start with irreducible polynomial representations of GL and C. These are parameterized by partitions of D with at most n parts, and these are known as Weil modules. And Sn sits inside the group of all invertible matrices as a group of permutation matrices. Now here's the open problem. You restrict the action of GLN to Sn. So W lambda Cn restricted to Cn. For example, you can ask how many times trivial representation of Sn occurs inside this. So there is no known positive combinatorial formula for this. But actually, Littlewood had one formula. By Littlewood's formula, we know that this coefficient has to be equal to the coefficient of S lambda in the expansion of H and Plethysm H. But as I said, monomial expansion of H and Plethysm H is very easy to write, but we do not know any combinatorial interpretation for the Schur coefficients. So for example, a sign formula for R lambda n, which anyone can write, which is very easy to write using the monomial expansion. This is just a sum over sine sigma and then Pn lambda plus omega sigma, where again Pn of so remember Pn of any vector is vector partition of that vector with at most n parts. So that is our formula for the this restriction coefficient. So there is anyway the open problem. So what is polynomial induction? So you look at the space of all polynomial functions on GL and C which are invariant under the permutation of rows. For example, this I have taken a 2x2 example, x11, x12, x21, x22. And if you look at this function x11 square, x12 square, x21, x22 plus x11, x12, x21 square, x22 square. It's a polynomial function on GLN2C. And you can check this is invariant under the permutation of the rows. So you look at all such functions, and GLNC acts on this space via the right translation action. So g dot f of x is equal to f of xg. And this is denoted by this int sn gln1. So there is so in this context you can define a notion of induction. It's called polynomial induction, which was defined by Narayan and Paul Prasad Srivastava. And they showed that if you look at the character of this module, if you look at the degree d polynomial functions on GLNC, which are invariant under the permutation of rows, that is a GLNC module, and the character of this module is basically the degree d part of H and Plethysm H. Okay. So now I will generalize this notion. So any polynomial function on GLNC can be written in this form: sum over CA x to the A, where x by x to the A I mean xij to the power aij. And now what I want to do is look at all the polynomial functions of degree d, which are again invariant under the permutation of rows. But I don't want to allow the row sum, any row sum of A to be 1. So I am sort of this inventing this notation, this int 1 hat sn to gln of 1. And you can show, it's not very hard to show that the character of this module is basically Hn Plethysm capital H, but H1 is missing, precisely because you are not allowing the row sum to be 1. So the character of this module is degree d part of Hn Plethysm H0 plus H2 plus H3 and then so on. So only H1 is missing. That is the difference between Hn Plethysm H and this character. So this is also not very hard to show. Yeah. Now there is one. So basically, I want to. So remember, this Baumann-Page has this stable Plethysm coefficients. So I want to connect this stable Plethysm coefficient to the notion of restriction coefficient. So how do I do that? So I use this technical lemma. I don't know what you are thinking looking at this proposition. Maybe you may find it hard or you may find it easy. I don't know. But yeah, this is equality of two different sign sums. So the left hand sum is over Sn plus 1 and the right hand sum is over Sn. Right. So what this is saying is that sum over sine sigma, and then you take the all possible vector partition of this vector lambda I plus sigma I plus 1 minus I plus 1. I runs from 1 to n. So that is a vector. And you look at all the vector partitions, look at the sine sum over Sn plus 1. That is equal to sine sum over Sn, where now you are looking at the vector partition of this vector, lambda I plus sigma I minus I, where each part has size at least 2. So this is a technical equality between two different sine sums. So using this, actually, you'll be able to show that. So this stable restriction coefficient that Baumann and Page they are looking at, this is same as this thing. So what is this? So this stable restriction coefficient. So I just recall. So you fix a shape lambda, and there you take your m and n to be large enough, precisely greater than or equal to mod lambda. Then the multiplicity of S lambda padded Mn in the Plethysm Hn Hm, that is same as the multiplicity of S lambda in the expansion of H mod lambda Plethysm with H0, H2, H3, H4, and H1 is missing. And you see on the right hand side, there is no M and N. On the right hand side of this equation, there is no M and N. So the role of M and N is not important once M and N are large enough. So that's a concrete interpretation of this stable restriction coefficient, that they are actually character of some module. So that's what I have written here, that if you look at the multiplicity of this while module lambda Mn, so as you know that characters of while modules are basically Schur functions. So character of W lambda padded Mn is same, the character of that is S lambda padded Mn. So I'm saying multiplicity of that in the representation sim m of Cn, that is same as the multiplicity of W lambda C mod lambda in this sort of funny notation that I have invented. It's int 1 hat S mod lambda to GL mod lambda of trivial, where by 1 hat, I mean that you allow all the polynomial functions on GLN where none of the row sums are allowed to be 1. And maybe it's not so difficult to actually see that this is actually a submodule. You can check. So this space is invariant under the action of GLNC by right translation. So this is what I call submodules with row sum not equal to 1. Yeah. So
I'm sorry to interrupt, but do you think you could wrap it up in like 1 minute?
yeah, I'll wrap it up. So that's what happened, and I'll just say one more lemma. So this is if you have a partition of Mn, and if your D is large enough, then you can show that partition of this vector lambda1 plus lambda plus nd with row sums, or you can say all the parts have size m plus d is same as the partition of this vector lambda1 plus n times d plus 1 lambda2 and so on, where each part has size m plus d plus 1. And using the stability of vector partition, also you can give a proof of this result. So Michel-Brion proved this result by some geometric argument, but you can also show using the stability of vector partition that this limit exists. And you can also show the similar thing for En Plethysm HM. So once your M and N are large enough with respect to the size of lambda, they also stabilize. So M and N do not play a role. So this double sequence also stabilizes when M and N are large enough with respect to the size of lambda. Yeah, and I think, yeah, I'll stop.